So that's about higher order derivatives. Well, as we will be defining the higher order derivatives of a function on a subset of Rp with real values using higher order partial derivatives of the same function, we're interested in the following thing. Now, if you have a function of several variables, well, if you form this partial derivative at A, if it exists, then this means you first take the partial derivative of f with respect to xj at A. Okay, well, you take it first, the partial derivative of f with respect to xj. Well, that again turns out to be a function of several variables of the same number, then with respect to this, and evaluate it at A. But you can also do that in the reverse order. Now we are interested when what conditions on f will guarantee equality between these two. That is, when is the order of partial differentiation interchangeable. So we'll start with the theorem which will tell us about that, give information about that question. Now let A be a non-empty subset of Rp, f on A to R, a function. Assume that A is an interior point of A. If the second order partial derivatives of f all exist on some neighborhood of A and are continuous at A, then the order of differentiation is interchangeable. We have that the second order derivative, del xi, del xj at A, this is equal to the second order derivative in the opposite order at A for all ij in 1 to p. Again, we will omit the proof of this, but you can refer to Bartle if you're interested in the proof. But we'll use this. Now, let's define higher order derivatives I'll do something redundant here. I will define it for 2, then I'll define it for n, but not in an inductive way. So the definition for n, that also will cover the definition for 2, and it will also coincide with the original definition of the derivative, the first derivative of f hat a that we had before. Well, again, we need something similar as in here. Let this be a subset of Rp, f on a to r a function. Again, we assume that A is in A interior, and the second order partial derivatives of f all exist and are continuous. On some neighborhood of A. So this is stronger than the condition here. Thus, in this world, interchangeability of the order that will be applicable. Okay. Now, the second derivative of f at A is defined as the map now its domain will be the Cartesian product of Rp with itself to R by so at H yz in Rp cross R now when we define the first derivative and then found its equivalent expression in terms of partial derivatives, it was as follows. The f of a at u is now replaced by yz. That was equal to the sum of the terms, the partial derivative of f with respect to xi at a times u sub I, the ith component of u. Now here, we will have a double sum over the second order partial derivatives, del xi, del xj, I from 1 to p, j from 1 to p, at a. Now this will be multiplied by the ith component of y and the jth component of z. This will be the definition we will adopt. Now, let us define the general form. Let n be in n. assume that the nth order partial derivatives of f all exist and are continuous on some neighborhood of A. The nth derivative denoted by dnFA of f at A is defined as the map dnFA. Now here we will actually take n copies of Rp and form their Cartesian product. N times with real values with dnFA. Now I will take y1 up to yn, and this at each y1 up to yn in Rp cross Rp. That is, each of these components, y super I, is a p vector, and we take n of them. This will be now here we will have n variables of summation, and we will sum over each of them. So we'll have an n-tuple sum instead of a double sum. So J1 from 1 to P, J2 from 1 to P, Jn from 1 to P. Here we will take the nth order partial derivatives of f. First, with respect to xj1, then xj2 up to xjn at A. And each such partial derivative will be multiplied by the corresponding components of the n vectors here. So we'll have y1, j1, y2, j2, yn, jn. Here, actually, the exchangeability of the order of partial differentiation, that will again be valid, because just take two successive differentiations here. Well, let's take the first two for the sake of expressing it easily, xj1 and xj2. Now keep all the remaining variables fixed. Well, then this reduces to partial differentiation with respect to two variables, the existence and continuity conditions, they are satisfied, so we can exchange them. But you can make every order possible just by exchanging each time in shot two successive ones. So that's exchangeability is also valid in here. And, well, this is, of course, just restricted to functions with real value, so it's not general, not on Rp to Rq, but you can extend this as well to that case by applying this to all the coordinate functions. But since we're interested in concavity, convexity, and the relationship of that with this, the version for real valued functions, that suffices. But if n is 1, then this actually reduces to the expression we had in characterizing the first derivative at A in terms of the partial derivative. So if there were no coincidence, then this would be an entirely different notion, but it's not. Now, some notational convenience. Now, write dn fa wn for dn fa. Here you have w, the same vector, n times. This just means not to the power n, having w n times. Now, we will need the version of Taylor's theorem fitting this higher dimension. Now, for that, let me remind you of Taylor's theorem, of one form of it in calculus. Now we take 2 points. Such that A is less than B, and this interval is entirely contained in A. And we also take some n in N. Now, Taylor's theorem, what it does is, it expresses the value of f at b, f of b, in terms of the value of f at a, the derivative of f at a, the second derivative of f at a, and that goes up to some n. Okay, now assume that I will now write it as it is in a standard calculus textbook. F prime, f n minus 1, all exist and are continuous on AB. But if this exists, then all the previous ones, they should exist and they will be continuous. So, but let's keep it like this. And Fn exists, the nth order derivative exists on AB. Now you have a remainder term in Taylor's theorem. You have its derivative form and its integral form, but here we'll consider the derivative form. Then there is some, say, gamma in AB such that f of b is equal to f of a plus, this is 1 over 0 factorial, then 1 over 1 factorial, but that's 1 again, f prime a times b minus a plus up to f n minus 1, the n minus first derivative of f at a divided by n minus 1 factorial b minus a to the power n minus 1 plus the nth order derivative of f, but in this remainder term, at some gamma between a and b, there exists some such gamma, divided by n factorial b minus an. Now, of course, the value of this theorem, it has a high value. Why is that? Well, if this is any x, then you have a polynomial in x minus a. Polynomials are the simplest kind of functions, and we know almost everything about them. So you can approximate each function which has the smoothness properties that Taylor's theorem requires via a polynomial function. So that's the value it has. Now, theorem Taylor the multidimensional case. Let A in R F RP now F on A to R a function. Now, actually, if we take, well, that was what we did in the proof of the last characterization, the derivative being non-increasing, that being equivalent to the concavity. Now, if we take two arbitrary points and just restrict our attention to the line segment, that actually makes it one-dimensional. Now, we will again omit the proof of this, but the proof of this will run, well, to make it one-dimensional. Forget about what happens outside this, and then reduce this to the one-dimensional case of Taylor's theorem. So let UV be in A such that UV, this is in A interior, and for each X in UV, all the partial derivatives of let me write it here, all the nth order. Here we can take n. All the nth order partial derivatives of f exist on some neighborhood of x. And let me write here and assume that for each x in uv, all the nth partial derivatives of f nth order, let me write it, okay, on x. Now, there is some u bar between u and v, that is on this segment, such that f of v now can be expressed in terms of the value of f at u, its first derivative at u, at some point, its second derivative, and so on. This will be equal to f of u plus tfu. This now will be evaluated at v minus u plus, now let me write one more term, 1 over 2 factorial, the second fu, v minus u, but now this looks like this, but this is just at v minus u comma v minus u, because this will be defined on rp cross rp according to this notational convention, plus up to 1 over n minus 1 factorial dn minus 1 fu at v minus u n minus 1, and plus finally 1 over n factorial dn f at u bar, this is the last term, and then at v minus u to the power n. Okay? Okay. What do you think is, again, from advanced calculus? Well, we have the Jacobian as the representative of the linear map, which we defined as the derivative of f at some point. Here we'll again have some representative map, but this time it will not be a unary representative, it will be binary representative, because we have on rp to rp for the second order derivative. What's the counterpart of that? Yes. For the second derivative? That's the Hessian, as you will guess. Now let's first define the Hessian. Well, we have, well, let me write that once more. Now, well, just to define the Hessian matrix, I don't need the interchangeability of the order of partial differentiation. Just the existence will be sufficient. We define the Hessian matrix H sub f of A of F at A by here we take the partial derivative of f with respect to the first variable, x1, and the first row will consist of the partial derivatives of the partial derivative of f with respect to x1 at a. That is, this will be the second f, del x1 at a. Then this will be this del x1 del x2 at a up to del x1 del xp at a. Well, and finally, the last row that will start with the partial derivative of f with respect to xp and take its partial derivatives with respect to the various variables, del 2f, del xp, del x2 at a, and finally this del xp, del xp at a. In fact, if you start with the function f, take its gradient, I guess that was defined in the homework you had last time. This is the Jacobian of the gradient. Okay? You take the coordinate functions of the Jacobian are, well, the first coordinate function is the partial derivative with respect to x1, the second with respect to x2. So this is just the first row, the partial derivatives of the first component of the gradient and the ith one, the ith component of the gradient. But now, let us know two things. Well, will this be necessarily a symmetric matrix? If the order of partial differentiation, if that's exchangeable, then it will be, because taking the second derivative, the second order derivative, first with respect to xi and then with respect to xj, that will be the same, taking the derivative in the reverse order. Now, in case the order of partial differentiation is exchangeable, H sub f of A is symmetric. Secondly, can we express the second derivative of f at A via the Hessian? That is, take the second derivative of f at A. This is defined on Rp cross to Rp at yz for any yz in Rp cross Rp. This will actually be this matrix product. Remember the definition of the second derivative? You take the second order derivative of f, first with respect to xi, then with respect to xj, at A, then you multiply that by the jth component of y and ith component of z. But this will be exactly equal to that sum. This will be 1 by 1 matrix, but the entry will be just what you have in here. So we have everything ready for our last characterization here. Theorem. Here. Let U be a non-empty, open, convex subset of Rp and f on U to R a function. Assume that the second order partial derivatives of f all exist and are continuous. On U. But this suffices to make the Hessian matrix symmetric. But if the Hessian matrix is symmetric, then we can talk of it being negative or positive, semi-definite or definite. Now, F is concave respectively convex if and only if h sub f of x is, for the first case, well, I will need the red, so is negative, semi-definite, and for the second case, positive, semi-definite at each x in U. For the strict versions, if h sub f of x is negative definite, respectively, positive definite at each x in U, then in the first case, f is strictly concave, and in the second case, it is strictly convex. Now we will prove this theorem, but we have more time left for that. But let's just consider, well, yes.
John, that is not an if and only if. For example, if f is strictly concave, do we have the Hessian to be negative definite?
The second one is not if and only if. And I'll give now an example why it's not if and only if. And in fact, we have given that example. We have considered this function, f(1) minus 1 to plus 1 into r, f of x equal to minus, say, x to the fourth. Okay? It is just this. Well, this is clearly concave and strictly concave. F is strictly concave. But let us consider its Hessian at 0. Well, here the Hessian will be 1 by 1 matrix, since it's just one-dimensional, and this will be the second order derivative of f with respect to x at 0. But what's that? That's 0. So this is not negative definite. So the converse, well, that will not hold. Well, it's like if for a function f prime is positive everywhere, for a real valued function of a real variable, then the function is increasing. But the converse is not true. The function might be increasing, but you, for example, like in y in f of x equal to x cubed, well, the derivative at some point might be 0. So this is the counterpart of that, actually. Okay? Well, we'll continue next Tuesday by proving this theorem. That will complete our list of characterizations of concave and convex functions. Huh?